So if we think, so Stefan's already talked a lot about account security, IAM account security, MFA and the like, one of those mechanisms by which he talked to you about was generally by way of these things called passwords, but so you probably focus already on having the responsibility yourself to deal with those things and keep these things secure. I think that's pretty obvious, okay? But, and yet there is another party that's going to be involved other than you whenever it comes to having an account with a username and a password, which is again, that going to be that server or that app or that thing that's actually storing that password in the form of some long term so that you can actually go ahead and authenticate yourself. That is prove yourself to that application, prove yourself to that website to which you claim to be. Now, in the simplest of forms, perhaps if you think of these servers, you are going to have to store your information on some kind of server somewhere and authenticate yourself against them. And inside those servers, you're going to minimally be storing your username and your password for which we've already registered with. Okay, we may be doing something very, very simple like this. For instance, if your website has, at the moment, just 2 users, at least, Alice and Bob, suppose just for simplicity that Alice's password is Apple, Bob's password is banana, you can imagine that a website or that app simply is storing all that information in like a very simple text file. These kind of key value pairs, if you will. Key value. Username, colon, and then the password, new line, okay? Something like this, username, colon, password, new line. And in fact, that's actually very, very common on how passwords are stored in systems. So at least certain operating systems like Linux, not necessarily as simple as this, but they often have a little bit more information to the side. But in essence, it is like this. It's just a username and a password. But let me tell you, it wouldn't be a good thing to see this, to store passwords exactly like this. Why? Well, suppose that this website, that this app, this database somehow is going to be hacked. It's going to be tampered with by an adversary, okay? So it's going to be hacked. Now, if someone gains access to this yellow file with all the known usernames and the passwords, well, at that point, they literally have everyone's username and password, okay? And we've already talked about kind of attacks like credential stuffing, whereby like one adversary will, once they know your one username or the one password on one system, they can then try and stuff those same username and the same password onto other systems, other websites, other apps, just in the hopes then that ultimately, unfortunately, you are using the same username and the same password elsewhere at the same time. So that's one very, very common attack, okay? They get your thing once, they try them in different places. So that's generally not a good thing if a bad person gets access to everyone's username and password. And of course, like in an ideal world, this stuff would never happen. We probably should, as administrators, as security engineers or the creators of the website, we should probably do everything we can to at least minimize the fallout, the damages that might result if, I dare say, this text file here is somehow compromised. So what can we do to protect this? What might we do then, rather than this? Rather than just storing Apple and banana in clear text, so to speak.
Yeah. Multi-stage encryption.
Right. So rather than having them literally as English words themselves, why don't we go ahead and employ a technique, like you say, multi-stage encryption, but this is broadly known as hashing. That if you've ever studied computer science too, you might have seen this phrase maybe in the context of hash tables or talking about data structures too. It turns out that this world of securing data is very similar. And in fact, this is a technique that's very, very common for solving a lot of problems. Yeah. So what do I mean by hashing in this context? Hashing is the process of taking in a password as input, let's say, and then converting that into a so-called hash or a hash value. Yeah. Now, these hash values, as you can see, they don't really look like English. They don't look like anything at all, really. They're typically just going to be strings of text. And those strings of text might have within them letters or numbers, but generally, they are going to be of some fixed length, generally, typically. And in this case, when we go about by taking our password as inputs, and then somehow, via an algorithm that we don't need to know or care about, some code that we might have written, we want to convert that password into a hash value. And then, crucially, we store that hash value. We take that hash value, and we store that instead of the password. We kind of discard that altogether. So the resulting hash value is what's interest. Make sense? Why? Okay, well, if you think about this as a proverbial black box, again, let's just stipulate right now, we've dripped this all down. I have no idea how hashing works, but what I do know is that a box can do it. Let's just imagine it as being this place on the page, yeah? So long as we can think about the process as follows, where generally speaking, there's going to be some input into that box, this proverbial hashing function that we don't need to know or care about. Ultimately, I want to get some output from that box. With me? And then what this box really is representing just a hash function. And you can think of this device as a box, some kind of machine, but it's going to be obviously some kind of program, some piece of software, or you can even think about it as some mathematical function which just simply operates on numbers, coming in as the input. It takes them and kind of rearranges them in some shape. And if you are mathematically inclined, I'm not going to use this sentence. I won't say this often, but you can think of that hash function as being represented like as f, a function. You can think of the input here represented by x, and you can think of the output of that being, the so-called process of f of x. If you're not familiar with that notation, that's fine, but that is directly related to this idea of hashing to math as well, if you might encounter before long. Okay, but what we do care about, at least from our context, is passing into this black box and having a password, getting out of that a hash. And what we said is we're going to store that hash, not the password. We take that and we leave this. Yeah, we kind of discard that into our new text file, into our new, into our own username of passwords. Yeah. So how might we go about by doing this? All right, so if I were to provide, for example, let's say the word Apple, because that's my password, as input to my hash function, let's think about the simplest hash function that's possible that doesn't output Apple. But again, what I'm trying to do is represent Apple so that I can eventually store all of that in the database. So suppose that I'm going to propose a very, very, very simple, maybe the simplest dumbed down hash function I can think of. Again, if you've ever studied computer science before, you might recall that you can hash those inputs on like very specific letters they're in. So Apple starts with A. So you know what? A is the first letter of the alphabet. Well, I'm just going to create like A is the first letter of the number. So I'm going to create a hash function that pictorially here just represents 1. So whenever the input happens to start with A, kind of like in a veneer, no, it's like a Caesar cipher, right? A does with apple as well with 1. Meanwhile, if you pass in banana, B for banana, I'm going to have the hash function output 2 because B is the letter of the alphabet and that represents that. Okay, and dot dot dot. You know, we might get to cherry or other passwords as well that I might put out 3 or beyond. And you can imagine doing this all day for all letters of the English alphabet, but pretty soon you're going to realize that this actually isn't the best hash function because it's fairly simple and it doesn't take a genius to crack it. And I can think of again some other problems too with this. If I go back to maybe A, think about avocados, aubergine, and other fruits that also begin with the letter A, that would still give me out the same hash value. And that's actually a characteristic that we might come back whereby you have a hash value. There might actually be some ambiguities. There might be some potentially, 2 inputs might have that same output. Okay, and we'll consider eventually what the implications of that might be. But for now, I'm going to say that's dare say a little bit too simplistic. So what might be better than just outputting 1 or 2 or 3 is perhaps something a bit more cryptic, a bit harder to read, perhaps, because that's just a bit too simple. That's too much of a hint. So that if I say your hash value is 1, well, if I know it's a 1, at least I know your password clearly starts with an A, yeah? Which is at best, I mean, I can do 1/26th the amount of work because I can discard the remaining 25 characters of the alphabet to just figure out what the password actually really is. So we don't want these hashes to be so revealing. We actually want the hash functions to look a bit ugly, a bit weird looking, and really just unguessable, as to not leak any information. So for instance, a very common older hash function for Apple might represent this. So .ekWXA83DHIA. So again, mixed uppercase and lowercase they're in. It looks weird, and it should do. You probably can't, and you shouldn't be able to make out any pattern within this. There is a fancy maths formula that we took in as input Apple, and then we outputted the hash function, the string of text right there. Okay, but this in and of itself doesn't, to me, leak any information like the number 1 or the number 2 or 3 might do. So we've already made an improvement in that regard. This is already better. And again, meanwhile, banana will look a bit like this, ZS4, ZH, and so on. Cherry, meanwhile, will look like that. So notice that these values are very different looking. So just again, maybe using this better hash function, I claim that doesn't just look at the first character of the alphabet when it comes to your input, but maybe it looks at all the characters in the alphabet, CHERRY in this case. We can probably come up with something more interesting, maybe more cryptic looking, if you will, like the values we've just seen. That's a good thing. Okay, so let me propose then that what we should do in our database, instead of storing passwords, is not store Alice, Apple, Bob, Banana, but rather store the hashes of Apple and Banana, respectively. So this would be what's in the database password itself. Yeah, I'm going to store this instead. Those exact same values that we just saw coming in as outputs from that black box, but at least in this case here, I'm storing that in my database of passwords, usernames and hash values. Why is this a good thing? Yeah, well, if you go back to our example, if someone now goes into your database and hacks it, perhaps, they gain access to all of your usernames and all your hashes in your database. Well, what they now don't see is an entire text file, sorry, I can't spell it this morning, of your usernames and all your passwords. They can't see that anymore. So they can't really go about as easily as just taking those credentials and then stuffing them into another system. Let's say, okay, well, that works for Twitter. Let's go about and see if it works for WhatsApp or Facebook or something else, Gmail. Just figuring out that database will give me access to accounts elsewhere. Credential stuffing won't necessarily work. I'm at least creating some work as well for the hacker. But at the same time, exactly, Jerry, you've nailed it. I've kind of broken the system itself, Jerry. And because previously, presumably, whenever Jerry goes into a website or an app and you type in, your username, it might be Jerry, and then your password, whatever that may be, what is the app ultimately or probably trying to do? Okay, because presumably, if you are going to be remembering this information somehow, once your username and the ones the password are going to be sent kind of over the internet, let's say, into HTTP envelopes and then into the server, well, that server is probably going to compare whatever you just typed in against that text file that it itself recognized, the database or the text file. And then the server is going to compare what I typed in as my password against whatever password is in their database. And that's the problem, yeah? Is that whenever you, as a user, you are typing in, your username, and we have the username still in the database, case in point, like Alice and Bob are still there, but what we don't have anymore is Apple. What we don't see in the file anymore is banana and so on, cherry. So it doesn't match because we've replaced these words altogether with these hashes. So that even if you type in, Alice types in Apple, we don't want to compare A-P-P-L-E, Apple, to this because obviously Apple doesn't look like that. It doesn't match. And as Bob's banana is that we don't want to compare banana against this because it's not going to match and so forth. So what can we do? Like we've locked everyone out, including ourselves. The way that authentication works, typically server-side, is when you're using hashing as follows. When you first create an account, or when you register again for an app or something, when you first type in Alice, Apple, Bob, banana, and so on, that username, Alice, and that password as well, well, that information is going to be sent over from client to password, from you to the server, okay? But what the server actually does is, before they are storing or saving the username and the password, is they're going to take it as the input. It's disappearing. So let's imagine this is your server, your database, okay? And they are going to be accepting as input your username and your password, but they're not going to store it as it is. They run it again through that hash function, okay? So whatever the username and the password results as a hash function, which of course like Apple is going to convert that into this value up here, and then it's going to then store just the username and the hash as well, the hash value of the password only. And then the password gets deleted. It deleted, it kind of forgets it from memory. Okay, so then what happens next is, well, the next time that that Alice comes about, that goes and logs into the website, maybe the next day, a week from now, whatever. Well, Alice types in her username, as she always does. Hopefully, Apple as a password. Apple hits enter, and then those two bits of information, Apple and Alice, they get then passed in this way too, as usual. And obviously, the server it can't just compare username against username, password against password, because it doesn't have the password anymore. Yeah, it doesn't have the password in the database. It only has a hash value. So what does the server do? The server does it again. It repeats the very same process of taking Alice's password, as inputted APPLE, runs it through that exact that same hash value from earlier, and then a year, a week, whatever later, compares the resulting hash value here with the one from before, and if they match, the resulting to whatever was stored in that database password of files that we say from earlier, then we know it's you. Okay, so we're swapping a ringer for a ringer. Now, admittedly, we are creating more work for ourselves. Does that make sense? Because we do have to do the same function again. There is literally more work to be done, but it's not that big of a deal sometimes because, again, this is going to be a math function, a bit of, or if you know how to program, just a few lines of code that's going to be written in software that converts password to hash values. And honestly, like nowadays, probably even rewrite it yourself, just using a library, some third-party code, someone smarter than us, maybe has written and gotten it right. So there's no bugs, there's no mistakes. You're just relying on someone else's code to achieve this goal anyway of doing that. Okay. So just to be clear, the upside now is that if this file were somehow compromised, if the server were hacked into or whatever, data were leaked, and if we weren't encrypted, at least now, well, you know the username on your system, but not what the actual passwords are. The password is still the thing that we've kind of hidden from you. Now, it turns out that those attacks we talked about before last time, I've talked about these things as well in kind of homework sessions that are still possible, that you can use, for example, a dictionary, of course, like for instance of English words, like real words, a dictionary of English words, and if you could, one fruit at a time, apple, banana, cherry, I can't think of a fruit that begins with the letter D, but each of those, run them in as values into the input of the same hash function as earlier, the library of code, whatever you're trying to achieve this, and then that's what's going to give you one hash value after the other. And then you can compare those hash values against whatever's in your database or the file or passwords that you, the hacker in the story, have actually might have stolen somehow. Durian fruits. Now, you do have more work to do because it's no longer as single as just comparing apple against apple and banana against banana, durian against durian. You do have some work to be done. You might have some computational work, and if the file's only a few values, of course, not a big deal. But if it's thousands or millions of rows, it might actually take more energy or work or effort or money. So again, we're just raising the bar, not keeping the adversary out altogether, just making it more difficult for them. And even if you don't have a dictionary yourself, even if the password's not all fruits in English, you can still, as a hacker in the story, resort to at least brute force attacks, where you can resort either the simplest of passwords like 00000 or 00001, and then just try to hash that as well and see whatever the resulting hash value of that is, and compare that against what's known in the password in the database. So try 00000. Hash it, compare. 00001, hash it, compare. See what's going on in the database compared to what you might have. Move on to the next one, the next one, the next one. Doing that not just for numbers, but also for letters as well. So A, B, and then hash that, compare that. So eventually, Apple will be on that list. Eventually, banana will be on that list too. But there too, there is the brute force attack. It's going to take some amount of time, some amount of effort. So, we're just increasing the cost, both financially and time-wise for the hacker in this particular case. And that's what we can at best do. There is another context too that's possible now in the context of hashing worth knowing about while we're here, which is a term of art that's known as rainbow table, which is a very beautiful way of saying that some hackers in advance, they might have already hashed all the possible English words in the dictionary. That is, a hacker might have already looked at all the different passwords of possible 4 or 5 or 6 or 7 or 8 somehow, something else, and then they've just got a big enough hard drive somewhere stored on on the cloud perhaps, and they've got this big table of sorts, this big Excel file, this big CSV file with all the possible words that they've ever tried, of all the passwords they've ever tried, and all the possible hash values that they've already computed. Then it's even easier because they don't need to go ahead and try a brute force attack per se, hashing and hashing and hashing. They can just compare because the work's already been done for them, because somehow a rainbow table, it contains all of the passwords that they've ever tried and then all the resulting hash values they've ever generated from that, and then just compare left to right whatever the user types in against the hash value that they've already computed. Now, for certain hash functions, the threat of a rainbow table is just not feasible. You might have petabytes of data, which means a lot of hard drives, a lot of money. So there is a potential downwards pressure on this kind of attack as well too. But it certainly just speeds things up for the hacker. Okay, and certainly if you're pre-computing, that is pre-calculating some of the hashes for at least some words of the English dictionary, certainly some short list like fruits in the world. Okay, I'm really interested in what Jerry's question was, because I want to come back to that. Another problem that we might come back to in the server with regard to your passwords. Is it possible for you to decrypt them? It is possible for you to decrypt the password, but I would rather say theoretically possible. Let me explain why though, okay? Because if you understand the logic behind it, or kind of the fixed hash representations, the way that mathematically makes that very, very, very unlikely that you would be able to, if you tried to, that is. Like you could, and you could even see this in the real world with what we call collisions, okay? Have you come across that term, Jerry? Just let me know. A collision, perhaps? If you haven't, that's fine. I'll explain. All right, good. So when we, because I might answer this, because if you, to explain this first, the problem that we might have currently on the server with regards to databases, yeah, so Alice might have Apple password, Bob might have a password for banana, but supposing that both Carol and Charlie, they've chosen Cherry. And just again, by cosmic coincidence, they've both gone for the same password, they both changed their password, and they're in the same database, as could be, because, let's imagine that this server has millions of users inside of this. Now, we've already concluded, I should think, that we definitely don't want to store these things in the plain text. That's a bad thing. Like, we don't literally want to store in the clear cherry, apple, banana, durian, because it's just too easy, for the hacker to do bad things with. So we at least want to hash this, we've said that much, but there are ways of leaking information. It's called like credential leaking, shall we say. And that's what Macy can do with buckets. But just to show you algorithmically, if I were to go ahead and use that same hash function from before that I've been using to hash apple and banana, now cherry, well, folks, what do we notice about Carol and Charlie's hash value? Ta-da! Curiously, but maybe not surprisingly, what have you noticed about Carol and Charlie's resulting hash value?
Identical.
Yeah, and after all, that's how hash functions typically work, right? Be it in math or software, in code, if you pass in the exact same input into that function, unless there's going to be some randomness going on, you're going to get the exact same output. Yeah, again and again and again. Now, why is that a big deal? Well, again, if you're a bad person, if you're a hacker, and if you're attacking this database, you've now got access to all the usernames and all the hashes, but we have leaked information in the sense that the hacker in the story, just by glancing this file, knows, okay, well, I don't know what Carol's password is, I don't know what Charlie's password is, but I do know that it's the same password. And that alone might be enough to go on the warpath to then figure out with high probability what it actually is. Again, just leaking information somehow. Maybe Carol and Charlie are related. Maybe they're, so if you just focus on words or numbers that are common to both those people, maybe there's information that's implied by some of this. They both like the same TV shows. They both like the same movies. They both like the same fruits. So, you can try in your mind's eye just to find any intersection of information that might relate to people that might lead you, again, with high probability to figure out without brute force, or, even what Carol's password is or what Charlie's password is. So this is a common a problem. Why do you think that those Facebook questionnaires are always asking you, like, what's your favorite Disney princess? What's your favorite fruit? Like, I don't think they really care, but it is of value to some people storing this stuff in a rainbow table. Okay, it's a real common problem. It's kind of it's tucked in there. I'm telling you, we only have 4 users in our database of databases. You can imagine this being, let's take Facebook for example, millions, millions, and millions more. Odds are, with millions of people, some of us are going to be storing the same password. Yeah, we can accept that to be true. In fact, I think without raising your hand or even admitting to this if you don't want to, do any of you have a password of, do any of you have a password with a 1, 2, 3 at the end? Maybe not in use now or circulating, but have you in the past have just appended 1, 2, 3 at the end of it? Or like a little bit harder, I know I did, 1 exclamation mark, just to minimally hit that criteria. Yeah? Yeah. Something like this. Again, maybe it's an account you don't care for or use anymore, but that is if you have, and if you can admit to this, that's a good example of where, if you have an account on the same system as someone else like me, then in that database specifically, presumably, that same hash value, that might be alone for us to have that intersection. It might be enough to leak and some information, just increase the probability that you, maybe not Alice and Bob in the story, but us, are going to be compromised with respect to our accounts. Okay? And like I said, this is, after all, if you pass in the exact same input, unless there's going to be some randomness going on, you're going to get the same output again. So what's the most intuitive answer to this? If you're going to get the same input and then run that through the hash function, we're going to get the same output.
Variable hash function.
Yeah, it's called something slightly different. It's got a better name for that. Yeah. So, is this what you mean, yeah? We can vary it. You can really introduce a little bit of randomness into it. There's another technique in the world that we can use to perturb that process, which is metaphorically, think of it like this guy here, just sprinkling a bit of salt into the hash function, just so we can vary what the output might be. So it's not random per se, but you are perturbing this output so that it's maybe less likely that 2 people with the same password are going to have that same resulting hash value. So how does it work? Okay, so in this case, like when we pass in cherry as the input, we got the same hash again and again and again. But now let me propose that we can modify the hash function to take in 2 inputs this time. So we've got not just a password, but also a salt value, so to speak. A little bit of sprinkling off, in this case, just 2 characters, 2 numbers, 2 letters, or combination thereof, something else into this. Now the hash function, which I'm describing, the box itself, we don't know what's inside, but it is just going to output ourselves our hash value. But notice, though, that it is actually different from the one before. Even if you don't quite remember what it was before, it wasn't this, okay? It's different. But worth noting here that in the output of this hash function is itself the salt itself. So the salt isn't something that's meant to be private. It's not meant to be secure or even, it's just kind of sprinkled in there just to make sure that whatever hash value comes out of this black box is a bit different than if you had put a different salt value instead. So for instance, this was Carol or Charlie, for cherry, we use different salts, okay? And that's the idea, is that different users should have different salts in case they choose the same password. So we get different results, okay? So instead of 50, let's suppose that Charlie, still going in with cherry as input. Cherry comes through. Charlie uses a different, say, 49. Again, 49 is not a number that Charlie or you and me would have to choose or pick. This is all done by the server automatically. But just picking a random number, like 2 characters, say 4 and 9, instead of 50. Notice what happens, though, is that if I rewind to Cherry with a salt of 5 and 0, this was the hash value. The first 2 characters of which are going to be the salt. If, though, and I change the salt from 49 or 50 to 49, the hash, the kind of remaining part here, that's completely different. That changes completely. And it prefixes that now with a 49 instead of a 50. So the point is that now Carol and Charlie have that exact same password, both going in with Cherry. There's no way that I, or the adversary, or Cherry, or anyone else is going to know how to decrypt it yourself just by looking at it. And indeed, like what ends up now in the file are now all those different hash values. One's going to be prefixed with 50, another one's 49, but the rest of the hash values are completely different. So again, the upside from this approach is where the hash function takes in 2 inputs, or maybe more, the password of the salt, and then outputs 1 hash value, means that we're not leaking information anymore. Except that collision case. There's one teeny tiny little area, there is a corner case by, if by chance, if dumb sheer luck would have it, that system chooses the same salt value for Carol and Charlie, well, there may be some leakage involved. And honestly, like, that may very well happen if you've got thousands and millions and millions and millions of users. You're eventually going to run out of those 2 character possibilities. You're going to have to reuse salt. But the idea is that we're just trying to put some downward pressure on the probability of being attacked successfully. We're trying to equivalently raise the bar to the hacker so that they're not as likely to gain access to my data or turn my accounts. Okay, and with that being said, this is what, generally speaking, hashes look like in the real world in practice. Okay, just for the sake of discussion, I simplified things, but I chose simple-looking hash functions that were using fairly simple short salts, like 2 characters, and then a fairly short hash value as an output. But in smaller fonts, no less, here, this is how Alice and Bob and Carol and Charlie's passwords would probably be stored. Nowadays, this is what KMS is. Okay, the key management service is probably going to be using a function, storing it with a much more recent modern hash function like that. And again, just by noticing at the length of this thing, gosh, this outputs a much larger value. And again, if you're familiar with the concept of bits, ones and zeros that are going to be used to store information on systems, those hash values are going to be using many more bits, many more ones and zeros, which you as humans might be familiar with seeing them as like alphabetical letters and numbers. But underneath the hood, they're no longer just ones and zeros. Those computers are now storing, which means it's much more or less likely that someone who also steals that kind of a file is going to be able to figure out efficiently what those original passwords are. And so you can see then too, for Carol and Charlie, even though their passwords are still Cherry, they're both passing the same input, those 2 strings at the bottom, they do look completely different, except in one location here, which is, it turns out that at least in this scheme, a lot of systems have kind of adopted that if you look between the dollar signs, like at the beginning, what seems to be the hash value, you'll see code like Y, $, Y, or the numbers as well as letters as well. Well, that's a little cheat sheet that tells the system exactly what hash function was used to generate the rest of it. And again, that's all in documentation. So smarter people than you and I have written this up and have made documentation on, like, researchers will do this. The documentation will be publicly accessible that you can read online, for any number of hash functions as well. So that is to say that when you create an account, when you go to a website, when you go to an app, if they are doing things in a good, consistent manner with the best practices and they're being mindful of your security, then they're probably in a file or a database or some other mechanism storing values that look quite a lot like this based on whatever password you actually, whatever sensitive stuff you're actually passing in. Okay? And in fact, just to give you a sense or a glimpse as to how easy or difficult it might be to crack passwords, okay? That is to figure out what they are based on just only hashes. So in the case of our first hash function, whereby we only had a very short hash, which was being outputted with or without the salt, there is 18 quintillion possible hash values. Now that's a lot, okay? That's bigger than most numbers. But again, with enough time, enough money, enough cloud computing, those early hash functions, they can be broken. That is, with enough time, enough energy, you can probably figure out what someone's password actually is by brute forcing it. And if you fast forward again to other strings that I showed you on screen before, the much longer ones that use more bits, so to speak, than you have this many possible hash values nowadays. I did actually look it up how to pronounce this, but based on just reading on my screen here, it's just a really big number, okay? But given how many digits there are on screen, given how many commas there are kind of here, this is a really big number, so that you and I probably don't need to worry about. We don't need to think about the bad actor being able to brute force and figure out how, and still being able to figure out by the end of time, essentially, what the corresponding passwords might be, unless there are some other weaknesses in your system, okay? Okay. Which brings me to this. Speaking of weaknesses, I think we've all seen this page, right? We've all ever clicked on your password. Yes, of course, those things. But have you ever clicked on a have you ever gone to a website that says forgot password, question mark, in the hopes of getting an email from this, and then, oh, there we go. And then that email actually contains your password inside of it? Has anyone actually had that happen to them when they've said that? Sure, Amos, yeah, so KMS really is just a management service, the key management service. And if you kind of peel back the branding from this, well, what is key material? I'll show you on the next slide, but key material is usually just using a encryption algorithm like 256 or other algorithms too. All that KMS is going to be a managed implementation of algorithms. That's it, okay? We don't see it as ugly as this. We just think of them as being keys, but they're not physical keys, of course. They're not anything that you can plug into a door. It's just numbers, and KMS will store those numbers for you and then do the resulting computation on your behalf. That's what the point is. It's a hashing application. That's exactly right, Amos. Because that's what it does, is it produces, if I go to the next page, it's this. Oh, well, just in a moment. Just kind of like separate those concerns here. If you go back to those recommendations again that we started from NIST, you think about cloud computing more broadly. So the National Institute of Standards and Technology, NIST, there is a recommendation here that verifiers shall store memorized secrets in a form that is resistant to offline attacks. Memorized secrets shall be salted and hashed using a suitable one-way key derivation function. So that's whatever it is, KMS or maybe yourself, but the purpose is to make each password guessing trial by an attacker who has obtained a password hash value expensive, and therefore the cost of a guessing attack with high or prohibitive. So when I refer to best practices in this case, I'm actually referring to documentation like this from NIST or from other companies too, that indeed those best practices amongst the goals for this as well, just to expose you to some of them, both on the consumer side, you, me as individual computer users, but also as well on the corporate side as well, when you might or you should be doing this when you're in a position of being responsible for someone else's data as well. So as for your question, Amos, like the actual hash functions to use nowadays, these are just some of them that KMS use that are generally recommended nowadays that can be categorized as being SHA-2 or SHA-3. And they are fairly sophisticated mathematical functions that, again, just taken as input, typically a password, and then more generally store an output of that hash value thereof. That's what KMS is. It's going to be using these things. There are other hash values too, other algorithms, should I say, that too can also be used to verify the authenticity and the integrity of messages as well, because KMS can be used for anything, right? In fact, today we're going to focus on how we can use primitives like KMS to make sure that data wasn't changed in transit as well when it's being sent over the internet from me to you. Data in rest, data in transit, in motion. But ultimately, yeah, I think maybe before we get into this, okay, we've got a bit of fun coming up. I think maybe that's a good point to just check in with you and say, if that's making sense so far, so good. Perhaps a good moment, space and time to just take a short 10-minute break. We can come back, get a cup of tea or coffee, and we can have a look at how they might output functions. Is that making sense so far? If you leave it with me, come back in maybe a few minutes' time. We can come back and see maybe more of this in a few. Just want to give you a chance to have a breather, okay? Oh, I'm here. Let me stop the timer before the whole house finds out. It's still incredibly early where I am. I don't want the time to go off. There we go. Good morning, everyone. Yeah, it is still very, very, rise and shine. It's still 6 in the morning where I am. So those that don't know me, I actually live in Brazil, of all places. That's why my eyes are glued together and I'm still waking up somewhat. So again, apologies for my tongue twistedness. It's because my brain's still waking up. I find it so hard to wake up in the morning at 4. There's a reason why the police come to your house if you're in trouble at 4 in the morning, because your brain is, less likely to be awake at that time of day or morning, night, whatever it is. Anyway, let's come back to what we were discussing. I'm going to get into this in a moment. I think this is a really good point to just be aware of what the goal is at hand, which is using fast-sign encryption. So this is going to be using server-side technology with KMS in order to encrypt something which we're going to deem sensitive and useful. Sorry, wrong lab. This one here that Macy can then go off and uncover. I'm not going to get into it right now. Just before we do, let's just talk a little bit more about, well, ultimately what we've been focusing on, which is what we've seen on this list so far is what we call one-way hash functions. I want to explain this up first because that is, there are mathematical hash functions, or in the context of this, these are functions written up in a code, languages in Python or otherwise, which taken as inputs a string of some arbitrary length. I trust you know what I mean. Basically, that is a password that's maybe this long or maybe that long or, whatever it is, it's arbitrary. But what's key to this cryptographic functions is that they output a hashed value of fixed length. That is always going to be this amount of bytes or this many characters or this many bytes of characters. It's always going to be the same thing out. That is, it doesn't matter how long or how short the input, the password is, but that is these one-way hash functions are one way in the sense that they can be taken in like infinity from one end. It could be really long or really small in that they take like an infinite domain and always, condense that into a finite range. Okay, taking a huge number of values, all the possible passwords in the world, and just to condense that into a finite set of possible hash values. That does carry implications. So it could be a really long list of hash values, but indeed, no matter how long that string is or how long that text might be, if it's of some fixed length, 16 characters, 32 characters, something else, there's only a finite number of those values. There is an implication of this, okay? So when you take in a really large input space into, and then map that in, or mathematically, like into a smaller finite range, so to speak, mathematically, it turns out that if you try to reverse the process, you can't, okay? There will be multiple inputs that yield the same output. Think about it this way, okay? If you've got yourself 100 passwords in the world, but you only have 10 possible hash values, okay? So 100 passwords, 10 possible hash values, you have to figure out how to put those 100 passwords into the 10 bucket, so to speak. Surely some of those passwords are going to go in the same bucket, okay? Think about that in terms of the English alphabet. If we're stuck with that original hash function where A was 1, B was 2, C was 3, Z was presumably 26, and we know that there's more than one fruit that begins with apple, avocado, aubergine, and so forth. So there too, if you're going to have multiple fruits that are mapping to the same finite range of values, of hash values, 1 through to 26, which means that if a hacker, in this case, or you even, as the owner of the system, you look at the hash value and you see the number 1, you don't know if the password was apple or avocado or some other word that starts with an A, okay? That's what I mean by it being a one-way hash value, because you cannot reliably reverse that by any means. Once it's mixed together, you definitely don't know what the original input was, okay? Now, there is a catch there, though, that technically means in some systems, it may be possible to actually log in with with Apple or Avocado, or more generally, your actual password and some other seemingly random password that might make no sense to you, but just because mathematically it has the same hash value, that password too might let you into the system, which is, but the idea is, because we're using really large number of bits, really long hash values, just the probability of me and you being able to figure out, or like a bad person being able to guess what that other hash value might be, it's just so small we don't really tend to think about it or care about it, okay? Now, this is all broadly what we call cryptographic hash functions, okay, which means that they have utility in the world of cryptography, where in the world of cryptography is really about the practice and the studying of securing data from point to point, really, when it's resting in your own system. And really, cryptography can be thought about the practice of studying your own data, particularly when we want to transmit it from one person to another one. So cryptography as a field can be broken down into a few different categories, one of which is the world of codes. And code here, not in the sense of like computer coding, that we might write in a language like Python or the like, nothing to do with software, but rather a mapping between what we'll call the code words and the actual message, or the true reading of what those words really represent. So here, for instance, is a book from some time ago that used to map those code words on the left, this column there, to indeed those messages, or the true reading on the right. The idea is that, if one party wants to send a secure message to another party, they wouldn't just write that out in plain English. Why? Because if that message were, written on a piece of paper or parchment, were intercepted by another person, that other human, assuming that they too know English, they could read the actual message, so the so-called plain text. But if you put that in code, you can convert the words that you try to say in code that make no sense necessarily to someone who's intercepted the message in and of itself to say, unless they had this book. Now, you can imagine this as being fairly time consuming, because when the recipient has that message, when they get it on their side, unless they've memorized all these pages, which looking at the size of it, I doubt it, the actual code words and the meanings are off, they do have a bit of work to be done flipping between the copy and the book to figure out what the message is. But the fact that they do have a copy of this book, even the fact that this book exists, is itself a potential threat, because, if one had their book stolen, then any of the messages that have now been sent can be decoded, so to speak. Just looking them up retrospectively can also do that. Also, any future messages too. If the owners of the book didn't realize that the book had been stolen, anyone could be able to see those messages and translate them. All right, so there are some terms of art here that I want to just worth knowing about, and you might use them in everyday context, not necessarily for the same purpose. So encode, what do I mean by that? So encode just means if you take it in plain text, be that in English or some other language, and taking that as inputs, producing the outputs of a code text. So that code text might be a shorter, more succinct sequence of words that might actually be English words also, but they're not meant to mean what they normally mean. Yeah. So code words or code text really are things that are meant to be looked up in a book cipher code, in order to figure out what message is actually trying to say. I mean, while decode, as you might expect, is the opposite of this. You take in this input of the code text you might have received as a recipient from the prior step, and then that same code book to then look at the code words, figure out what the actual message is in order to get that original plain text out. Now, there is an alternative to codes, which is, if only because code books can get really boring to use, they can be taken and compromised and the like. So not necessarily the best system in the world that we need to keep physically keeping a physical book like that secure, or let alone do anything efficiently when converting. So there are what we'll call ciphers, and ciphers are a bit more algorithmic in nature. So if you've ever done a computer science class or like a programming course, you already have a predisposition to thinking algorithmically and taking a big problem and breaking that down into smaller pieces and then applying some kind of logic, sometimes again and again and again, just to solve the same problem. So ciphers focus on exactly that. They don't focus on maybe the words or the phrases. They might focus instead on the individual letters or the characters they're in, instead of, or like bits perhaps, even if it's in the context nowadays of ciphers. So this is actually from a movie that I watch at Christmas. So you might have seen this in pop culture. For instance, this is a frame from a famous TV show, if anyone does know The Christmas Story. Plays like every day, a couple of TV channels around Christmas time, where this is Ralphie from the movie, one of the main characters from the film, and he has in his hands the secret decoder pin that he tried so hard to get through the mail, and the secret decoder pin was from little orphan Ellie herself. Okay, so this does implement mechanically a cipher. You see this in pop culture as well with James Bond. There's actually a video for this, which is kind of funny. This is from Skyfall, a supervillain who uses supercomputers to track down and take down MI5, MI6, and this presents technology in a range of ways, from stolen hard drives to top secret files on them. And this is something called polymorphic encryption. I don't know either. I don't think it's real. Suffice it to say that if you're a James Bond fan, you probably enjoy smirking at the ways that technology, including encryption, is misrepresented here in Hollywood. Skyfall's a good one. Of course, they all seem to cascade and rather magnanimously show you a tube map. Of course it was, all along. Of course it was. Anyway, if only you mentioned the Enigma machine, because that is an incredible topic. So World War II.
And that's also a fantastic film, one of my favourites.
Oops. Sorry, adverts. Yeah, it's a great movie. The Imitation Game. Have you had a chance to visit the Bletchley?
No, I mean, we're going to go next year.
But if you can get the chance to go see it, so first,
we're both kind of military history nerds, and I love all the like stuff about the Bletchley Park, the bomber, the original bomber that the Polish created pre-World War II. And then you've got obviously the one that he made, the big what did he call it now? It was called the bomb, the actual one. It wasn't called something else in the film, but it was actually called the bomb.
Is this a bomb, like in the bomb sensor bomb or something else?
Well, no, the Polish one was Bomber, BOMBE. That was the one the Poles made pre-World War II.
I see, yes.
There was 4 Polish mathematicians, and they literally created a machine that was able to decrypt Enigma. They smuggled it out before Poland was invaded to the British.
Yeah, that reminds me.
And then, but the Germans changed Enigma and added an extra rotor on their Enigma machine.
They have a section of this in the museum if you do go to see. They
Yeah,
do
so
have
they
just
actually
that.
made that's it. Marian Rejewski, he created the original bomber.
Sorry, it's in the wrong language.
He was one of
It's
the guys who created the original bomber. The
ah,
Germans made it harder by adding an extra rotor
yep.
to the actual machine. So that's why they had to create the actual physical what do they call the actual computer? The one in the film that he goes puts all the code stuff in. It wasn't
Uh,
called what it was called. It was called something else than what it was called in the film. I think it was called Turing's bomber, but I could be wrong.
they probably use maybe some code word for it too.
Yeah,
If
you see
anything,
the Enigma machine there's got the three rotors.
yeah, yeah.
In the actual when it came to World War II, they actually had an extra rotor. And then there was one called the Lutz machine, which was like the high command used. It had five
Uh-huh.
rotors.
Uh-huh. The ones on U-boats and some reason are like
Yeah. Sorry, everyone. I'm a bit of a
fascinating.
military history nerd. I kind of got a bit of a tism then. Sorry.
You're gonna love Bletchley Park if you do go. I've been twice, and there's so much to it. You can't do it all in one go. They have like a Radio Shack too, where you can see kind of if you're into that sort of things too. People will take the time and explain things to you in practical senses, and I love it. I had the best time ever. Please do go to Bletchley Park.
I say we're looking at doing Bletchley, Duxford, Hendon, and the
yes.
Imperial War Museum all in one. We've got family down there, so we can do a weekend of it and just go down one weekend and just go bang, 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 just go through it all.
The Imperial War Museum do that a lot of that too. I'm into that as well. This is the film is a good representation in it. I think I had a video here. It might not be the one we're thinking of. Of course, Voldemort's talking down to our boy Benedict. Oh no, sorry, no, it's Charles Dance, not Voldemort. On our finds. But if it's not familiar to you, this machine here, what we just pointed out, is a mechanical implementation of this idea of the cipher. It's a kind of smaller picture, but you can kind of make out, instead of using maths or gears, just turning this way or that way, it was much more mechanical in nature. Like it wasn't anything that we plugged into the wall. It was with rotors and lights and the like too, but it was still implementing a cipher that could be just configured with different inputs actually to influence exactly what the output should be. The problem in the movie, and Rich pointed out, is that it lasted, or like it would change every day, right? Like midnight.
They wrote to start at a set position, so a set of 3 letters. They changed it every 24 hours.
Yeah.
So the big thing they had in the film, if you ever watch, and I recommend everyone watch it because it's an awesome film as well, but it's good history knowledge. They broke it by one guy putting the same 3 letters at the start of his girlfriend.
Yes, that's it.
That's the scene where in the pub he just goes, they've just lost the war, throws a pint at a lass and runs off to try to get the machine to break it.
Yeah. Right, and this is back to this idea of leaking information. If you give a person like any opportunity, they will take it. Like we said, when it comes to having those salt values and they can represent the same, if hash values are going to be stored minimally the same, that can then you can extrapolate things from this. In the context of the Enigma machine, like they were able to recognize that the letters would be signed off with HH at the bottom of the top. We know what that is, but that was enough to tell you at least, well, H is going to be this particular number, and we can then from this deduce other parts of the letters also.
Well, it was a 6 a.m. message that they had small ships in the North Sea of the Germans, weather ships. And the deducer, all he's got to do is look for weather and then HH.
Mm-hmm.
And that would give them the key to break the code. Because the computer they programmed to look for those 3 letters. So it ignored every other possible outcome that could not produce those letters and then tested it against the machine.
The cryptanalysis. This is the Imperial War Museum does a good job on this too. So, you're gonna love it. You can actually visit that room as well. That's where that scene was filmed, by the way. This little scene here.
Yeah.
This is this room, which you can go and visit. It's there. So, the amounts of, and this is again pre like World War II era, like before the advent of the internet, and the like, where an encryption method with just 3 rotations would have been up in the billions or trillions or something. Truly mind blowing and thought the fact that it was reset nightly by the Germans too, which meant it was also there was social downwards pressure on the time that was involved in order to do it. Your work was reset daily.
And also, you see where the keyboard is with the typing underneath that, there was like plug boards, so you could actually plug those in to change how the class was routed as well.
Yes, and that
would
would
worked out. It was something like it was 1 to the power of 42 possible permutations. It's some mental number. You look at it and just go, nah. And that's used to break it using crib sheets.
How many permutations were? So you're right, that switchboard would be reset daily because the same keys were used, but the codes or the rotations would be changed.
That photo there shows us the actual plug boards. That's an old one with only the 3 rotors.
Mm.
So if you think you had a 4th rotor onto that, that's what makes it so crazy.
Up to 4, right. So A becomes D, D becomes F, F becomes G, and it seems simple, but when you're trying to do this against the clock and having so many different possible keys being reset nightly to mask your communications, no less, it was considered humanly unbreakable, unless you had some other counter machine to be able to count or permutate through this, to brute force it. Up to 5 rotors, apparently. Gosh.
Yeah. The 5 rotor was the Lutz, and that was like what the German high command used to send out messages to, like, say, from Adolf's bunker to, like, the commander of the forces in Russia. He used the Lutz machine, and that was Enigma, but even more.
This is all again the way that we're building this story to be is cryptography is a science of number crunching and really throwing bigger numbers against other ones, so that you would have also this other number that would have to fight back with, which again that they're like examples of physical devices too. What we're thinking about mostly in terms of cloud as well is on more things digital, but the same idea as Enigma, really, just that things that you can ultimately, for instance, now implement most scalably in software. The words we're going to use are all the same. That is to encipher a message, to take that English word or other language and also into so-called plain text, convert that into, not surprisingly, ciphertext as the output. Meanwhile, the equivalent term, as you might know, is also encrypt. Same idea, synonyms for our purpose, encipher, encrypt, encipher to encrypt. Nowadays, probably encrypt is the most common of those terms. Meanwhile, decipher would be the opposite of this. Actually taking that ciphertext someone else has sent you and run that through an algorithm or cipher to get back to plain text. Meanwhile, decrypt would be the synonym for that phrase also, which refers to exactly the same process of taking the ciphertext as input and outputting plain text as an output. So the resulting net of this is how do we configure those ciphers so that you and I can actually use the same algorithm, but customize them also. Not only with their own messages, but also with their own settings too, that just so that because you and I might want to send the same plain text, doesn't mean then that the ciphertext has to be actually identical. So the world of cryptography too, it's quite recommended that you and I use public and well-documented, well-tried and tested, battle-tested algorithms publicly, where we do keep one part of that information secret, so that for our use of the cipher, that algorithm is going to be specific to us. And then this customization, this choice, this configuration are generally thought of as being in terms of keys. Now, like, how a key nowadays, a physical key might lock an actual door to your home. Well, a key is what unlocks the capabilities of that particular cipher. So it's the key that needs to be known and needs to be just used not only by you, typically, but also by the recipient also. So by you having copies of keys of the same key, not only can you then encrypt messages, but also, or encipher them, but also decrypt or decipher the messages too. What do the keys look like in practice? Key Management Service, KMS. Well, KMS isn't physical. There's not actual keys, okay, in the sense of virtual worlds. They're really just going to be big numbers in KMS. And often, in KMS, you're going to have very, very, very big mathematical representation. Like, there's going to be some significance to those numbers. Sometimes they don't even look like numbers. They might be presented to you as a phone or a laptop as letters of the alphabet, or maybe with punctuation as well. But at the end of the day, they're just really big numbers, which of course, if you know a bit of computer science already, they're just zeros and ones. Perhaps more useful to think about them in terms of metaphorically as a key, physical key. I think that's just easy to work with. The way that they're actually used is, so within the world of cryptography, there are different types of encryption. The first one we'll look at is one world of secret key encryption, which the presumption is that the security of your data relies on the secrecy of the key. Okay, you have to keep your key a secret, so that if I want to send a message to Richard and then Richard sends it back to me, we must keep whatever key that we're using to configure our choice of algorithms a secret. What do I mean by that? Well, specifically, the secret key cryptography. Well, I've got this is symmetric key encryption, okay? Specifically in the context of encryption and scrambling up data, that's known as symmetric key encryption, for the reasons that both A and B, both parties involved in this story, are going to use that exact same key. It's symmetric. It's like a mirror, yeah? We'll contrast that in a bit with asymmetric in a moment, but solves other problems as well. But right now, as it is, just to focus on the process of encryption, I'll send this a link over as well before I forget. Just like the process of hashing was before, as being this black box right now, somehow or other, this black box is going to be able to encrypt information for us, okay? So we're going to be taking an input as plain text, hopefully, fingers crossed, outputting my output as ciphertext, so that actually I can send over the internet some other kind of channel as well, the recipient there too. So in the context then of secret key encryption, cryptography, gosh, tongue twisters, the picture looks a bit like this. So not only do you pass in as input to the algorithm your plain text message, in English and some other language also, but you also pass in a key. As for now, just think of this key as like a number, something that you or the other person have now agreed upon in advance. Yeah. So this key, this algorithm, will ultimately output your ciphertext. So just to be clear, the motivation for this key is so that if you and I, or you and you, we're all using that same exact encryption algorithm, it's going to be obvious if and when we're using that same message because, as per our discussion of passwords, that would leak information. Maybe you don't want information being leaked, but it's probably a good thing if, just because someone else is getting that message, it makes it more likely that a bad person can infer what it was because the ciphertext just happens to look the same. So instead, we want our ciphertext to be unique to each of our transmissions. So just go for a simple example. Suppose the message I want to send to you, I want to send you the letter A. Okay, that's my message. Suppose another key I'm going to use is just as simple as the number 1 in that case. Okay, not best practices, but we'll just use them for the sake of discussion. Let me propose that the simplest algorithm I can perhaps think of is actually one that would take A as input and output B. You might be able to see where this is going. Okay, Proton Mail would use a much more sophisticated version of what I'm about to get to here, which is if I provide B as input, as 1 as the input as well for the key, as plain text and the key respectively, the output would be C. So believe it or not, many, many years ago, Julius Caesar was a man who would use an algorithm like this, whereby this algorithm, the Caesar cipher, is generally what's known as a rotational cipher. Because again, if you are rotating the letters of the English alphabet, A becomes B, becomes C, C becomes D. I bet if we continue this logic then, Z goes around and wraps up around becoming A as well. Now, of course, this is being applied at the moment just to very short messages that are not that useful, A, B, C. Sending one letter at a time is not particularly useful in general, but again, just demonstrating to you how we can encipher, how we can encrypt our plain text into ciphertext. That is, when you now receive this message, let's say on the other side of this envelope, not only do you now need to know what algorithm to encrypt it, in this case, if we're using Caesar cipher, we need to agree on using the Caesar cipher or rotational cipher more generally, but you also need to know what key we agreed upon as well, how to make sense of it. And the key might not be as simple as just 1. For instance, here is a key of 13. Yeah. So if your key is 13 and your plain text is A, your ciphertext should be N. Okay. Because N is 13 places down. So A, B, C, D, E, F, G, H, I, J, K, L, M, N. So now your algorithm uses it's a little less obvious. 13 is also representative of something that's now been known as on the internet as rot 13. So rotate 13 places, which is a popular way of scrambling information, but Also, not in a way that you intended to be really secure. You know, often it was, so back in the day, this was used for like movie spoilers online. If you ever wanted to make something like The Matrix did this before, before there was CSS, before there was blurring effects on the websites and whatnot, you could just scramble it up in a way that just looks completely encrypted, but also not that difficult. You know, it's very easy for someone as well with a click of a button just to decrypt it back. Okay. However, I would recommend that you don't use a key of 26. Why? Any thoughts? Why?
A becomes A.
Exactly. At least in English, there's 26 characters, A through to Z in that case. So a key of 26 would just output for your ciphertext that exact same thing as your plain text. There's actually a joke on the internet whereby ROT26 is twice as secure as ROT13 because, you know, 13 times 2 is 26, and obviously that's not the case deductively here. But of course, this particular algorithm, like keys of the small size, 1 through to 26, not secure at all. Bad idea. Why? Because honestly, like, I don't even need a computer to crack this code. I could probably take out a piece of paper and a pencil, just try all the possible numbers, 1 to 25. I don't even need to waste my time on 26 and figure out by a brute force what keys might someone use in order to send a message like, you know, this for that algorithm. And not even on single letters either, but maybe on like it operates on every single letter of the message. It wouldn't take me that long to probably just figure out just by brute force, by hand, really. And with code, my gosh, like some Python code could probably do that even faster. So this is on screen right now, but a ciphertext that I created in advance, which I'm going to stipulate right now and put into chat, is using that same rotational cipher. But I'm not going to tell you just yet what key I actually used. Okay, I'm going to tell you right now, it was all done in an English word, all using capital letters. The task now at hand is, how do we decrypt this? So whether you are the intended recipient or maybe someone else maliciously, you've now intercepted this message, this transmission, this message. Now you're trying to brute force your way through it by trying, by the looks of it, you know, to get through to it. I bet we could also brute force our way through this algorithm, but why and how? So how does the decrypting process work? We do the same thing, just in reverse, okay? So if this is our picture now, where you have your ciphertext at hand as your input, you should be able to pass in that same key as the input, again, 1, or for instance 13, or for no good reason 26, to get back out the plain text. But of course, the decryption algorithm is the opposite, where you don't just want to add 1 position or 2 positions or 3 positions. You want to subtract 1 or 2 or 3. Okay, you want to go in reverse, so to speak. You want to go backwards. So if I want to pass in B into the ciphertext and 1 as the key, well, the plain text or the decrypted word should, of course, be A. Okay, 1 away from B takes me back to A. And so that holds now for all the other letters of the alphabet too, assuming I'm reversing the process in order to decrypt. I'll give you just a moment or two just to glance at the screen, see if you yourselves can't figure out what this ciphertext is trying to say. Because if you like this idea of figuring this out, if you want to get better at this particular skill, you are what's known as an aspiring cryptanalyst, which is, you know, someone that works in this world of cryptography. All right. I'm going to reveal it in a few more seconds, but if British got this.
Yep.
Drum roll, please.
What is the name? His twin daughters. And a 1 and a 2.
Yeah, exactly. Oh no, my link didn't work. And the drum roll there. All right. Yeah, and 1 and a 2. So stupid joke, but that's the idea of play. All right.
Quality dad joke. It's a quality. That's dad level joke. That is perfectly fine.
It's better if you know it's coming. And that's it. This is you know, whatever the message might be. To move on with some actual algorithms. I mean, obviously, the rotational cipher is not a very good one, used 2,000 years ago, so not to be recommended. Good for demonstration sake, good for discussion sakes, but it's not something that you should be using in practice unless, you know, trying to send a love letter to someone, they want them to read it back. But, you know, the level of security that you and I are trying to get to is, let's say, a bit harder, okay? In the real world, the phones, desktops, and the like, generally using our AES or triple DES, which are the popular algorithms today that have been vetted by the world and are very commonly used by secret key encryption, symmetric and encryption ciphers, which, again, to be clear, symmetric encryption, it's the same. The sender and the receiver both know in advance, they both use that exact same key. But this is actually, well, there is a problem to this, okay? So that even like in the world of secret key cryptography or symmetric key cryptography, it doesn't solve all our problems. Because I've kind of taken for granted one thing throughout this whole discussion, which is that the sender, the receiver, you and me, we have a shared secret between us. Whether it's a simple key like 1, 2, or 3, it doesn't matter, hopefully not 26. But there is a kind of chicken and egg argument to this. There's a problem to be solved, so to speak, because how do you actually establish a shared secret between both parties, A and B, if we've never talked before, okay? So for instance, if you're going to Amazon.com, for example, for the first time, you know, or Gmail.com or whatever it is, Proton.com, ideally, you probably know this already just having lived in the real world nowadays, you want a connection to Amazon, you want a connection to Proton or Gmail to be encrypted, you know, or scrambled up in some kind of way. Well, why? Because you don't want your password to be stolen by anyone, obviously. You don't want your credit card information to be intercepted by someone. You don't want your personal emails to be read by the people. So it stands to reason that encryption is generally a good thing. And maybe you've seen this again from the URLs, in the URL bar by something called HTTPS. S literally meant to be secure. But odds are that you don't know anyone yourself personally that works at Amazon or works at Gmail or works at Proton.com. So what key is it that you're using to communicate securely within those websites? How do you get to Proton? How do you get to Gmail? How do you get to, if not, you know, new websites that don't exist today but might come online in a few minutes from now, okay? How do you establish a shared secret with someone you've never met before? Okay, that's a fundamental gotcha. That's like a caveat to this whole symmetric or secret key encryption thing. It's fundamentally flawed, okay, which assumes that you have a shared secret between someone. Yeah? There's no, I can't see the illustration here. I don't know what that's referring to. But that's why I went back to this one, where you have decided ahead of time on what rotational cipher you're going to use. You have a shared secret between you and the other person, but in that chicken and egg scenario, that comes where the only way for you to establish the shared secret is to send that secret to the other person securely. But if you can't communicate securely, then you can't send them the shared secret. So now you're kind of caught in that deadlock. Thankfully, again, thanks to maths, there are some magic ways that we can get around this, and we can solve this too, not via symmetric encryption, but what's better known as kind of envelope encryption or asymmetric encryption in the world of public key cryptography too. Okay, amongst the algorithms that might be in use, something called Diffie-Hellman, MVQ, RSA, others as well. I dare say on this list, like RSA, I think we've talked about Rich before, is probably the most well-known. I think that's, you mentioned this before, right? Something you might have seen in the world. Have you ever come across this channel, this YouTube channel, Computer File?
No.
You'll love it. It's a bit nerdy, but they have, the University of Nottingham does a great job of kind of drawing this out and showing you, which I'm going to leave that for another day, okay? Just in the world of public key encryption. I'm actually going to refer to another video in a moment because they do a good example of demonstrating something that I find a useful scenario. So I won't show you the whole video now, but just to explain what the point is, okay, of asymmetric key encryption, this is what we're going to see in KMS. Again, KMS is just a way of managing this, but the fundamental idea is the same. It's implying in asymmetric or public key cryptography is that you don't use one key, okay? It's not the same key. It's asymmetric between both people A and B. Okay, so you're actually going to be using two keys. In the world of public key encryption, everyone in the world has both a public key and a private key, yeah? So it's asymmetric because we're using two keys, and those, and they're not real keys, obviously, they're just really two big numbers. Okay, there is a mathematical relationship between those two numbers, the world of the public key and the private key. But that's a relationship that your phone or your laptop just figures out when you generate those values for you. So unlike our discussion of passwords, which you and I as humans would need to choose or memorize or store that in our password managers, when it comes to keys and KMS, those are generally, like in the world of public key cryptography, KMS generates them for you. And as the name suggests, the whole purpose of KMS is to tell the whole world that if you want to know what your public key is, it is in no way a secret, okay? You can literally publicize it. You can email it out. You can put it out there to the world, put that in the signature of your email, put that on your website, social media. The whole point of the public key is that it is public, okay? So one part of it's public, but suffice it to say that there are two parts. The private key should be kept a secret by you, okay? By your own device. That should never, ever, ever be shared by anyone else. So your private key stays private. The cool thing about public key cryptography and the mathematics kind of underlying this is that if you share your public key with someone else on the internet, if you put that to your social media, and you see this, people, people do this. Very, aficionados will put that at the bottom of their email addresses. Use my public key. They will use that public key to encrypt a message, and then send that over to you via email or by chat or by other technologies too. And again, if you had to guess, if you had to guess, what is the only key in the world that can decrypt a message that has been encrypted with your public key? Okay, so the only key in the world that can decrypt a message that has been encrypted with your public key is, of course, your private key. Okay, that's what that mathematical relationship ultimately does for you. Which, so pictorially here, this is why our algorithm implements this idea of public key cryptography, which is, so let's see what the input to the output should be. The goal is, if I'm to send to you a message and to have shared with you this public key, whoever is sending you this message uses your public key, okay? That's your plain text message, so to speak. That's what comes out as the ciphertext. So this is how asymmetric encryption works. Meanwhile, like when you receive that message on the receiving side, you then use your own private key. You plug your private key in and the ciphertext that you just received to get back your plain text. This is what we mean by asymmetric. So unlike secret key cryptography or symmetric key cryptography, where you're using that same key, symmetric key, for the same key, back and forth, +1 or -1, in the case of the rotational cipher, with asymmetric encryption, you are using one key for one process and another key for the decryption process. That's what's so fundamentally different. And RSA is maybe the most popular algorithms out there. Your browser will use this. You've been using some variant of RSA all your life. I'm not going to go into great detail for this, but maybe one of the most important details about RSA is that it relies on really, really big prime numbers. So in fact, in a nutshell, what happens with RSA is that your computer or your phone, it chooses a really big prime number and calls it P for prime. It then chooses another really big prime number called Q. It multiplies them together to get a new value. I'm going to call that new value called N. This is the dot product. So it uses that new value, N, in the resulting mathematics. In your algorithms, authors come up with, dot RSA. The presumption is that when you take really big prime numbers and multiply that against another equally big prime number, it's really hard for you to figure out the product of those two numbers, okay? What the original P and what the original Q are. You mix water and wine together, okay? Again, if you're, basically you multiply them together, you get really big numbers. RSA is one of the most popular algorithms out there for this, which is, well, the rest of the mathematics I'm not going to get into much, but in essence, this will be probably the scariest looking formula I will ever talk to you about, okay? So the value N, I just described a moment ago here before N, that is going to be used to divide essentially, ultimately, if you're unfamiliar with mod here, modulus, that means in this context just to take the remainder of some value. So what we're looking at here, what we're doing is a quick summary of how encryption and decryption works in RSA. If you have some message M, if you want to send to another person and you may have come up with somehow before, by the ... process earlier I alluded to, you might have come up with your own public key E there. Well, then someone, can take their message, encrypt it by raising the message to the power of E, and then the exponent of E, and then divide that again, divide, figure out what the remainder is, divided by N. That gives you a value so-called C for ciphertext, and when you receive C, you then use your own private key, again, known as D here. it raised the ciphertext up to the power of d. That is the exponent d. In this case, you divide by n in order to figure out what the remainder is, and which will then give you back the original message. Now, that is an oversimplification of this, but in essence, that is what the RSA algorithm is. It has to do with picking two very big prime numbers, multiplying them together, smashing them together to get that value n, and then using n as well as some of the values to ... generated by that algorithm for you in order to encrypt and decrypt messages ultimately. And this is generally what's known as modular arithmetic, which is a lot of division, a lot of division, a lot of division in order to come up with those remainders. Ultimately, KMS does this for you, okay? It's a very common way to asymmetrically share information without having to agree on one shared key in advance, using a public and private key instead. There are other techniques too that have come up in this world of public key cryptography, which is known as key exchange. So by contrast, if you do actually want to establish some kind of shared secret, there are other algorithms that are different that humans have invented over the year, Diffie-Hellman as well being one of them. So to figure out, again, using fancy maths, how both A and B come up with the same value that they then use as a shared secret, but without anyone else who intercepts any of those messages being able to figure out what that shared value is, that shared secret. The essence of the maths here is, again, if you first pick a value G, G for generator, that can be as simple as number 2, for example, and you pick a really big prime number, call it P here, P for prime, that refers to those agreed upon in advance. Meanwhile, person, say A for Alice, she picks her own private key, which is just going to be another big prime number, and then does the maths. G to the power of A, mod P, again, mod refers to taking the remainder modulus of some value. Meanwhile, B, Bob, does the same thing, uses the same P, but picks his own private key called B, raises G to the power of B modulo P, and that gives him the results of capital B, whereas Alice had A. It turns out then that you can send those values over the internet, and one way or another, you know, again, I'm not going to worry so much about the maths of this, but if you were to take a high level class on this or just kind of look at the theory behind it, there are rabbit holes by which you can then go down to better understand how the software really works, how KMS really does this. But just know that there are shared secrets we don't need to. It's generally best practice for us to stand on the shoulders of people that do this best, you know, that has been vetted by the industry and academics as well. So I don't really know how to explain it to you more than just assume or just trust the technology, trust the ones that have been tried and tested, rather than trying to come up with your own crypto system, so to speak, you know, that may very well have faults that you yourself do not know. The icing on the cake here is that ultimately, if you're curious as to the underlying maths behind this, what value ultimately both Alice and Bob are calculating, G to the power of A, B, modulo P. This is why I'm referring to this class here, which is phenomenal at explaining this. Come on, after 10 seconds of force-fed media, we're eventually going to get... He demonstrates this in a really cool way, which is with, again, like if you can visualize this as having the information sent over the internet, you kind of mix them together and you can know one part of your number without knowing the other one. Okay. Anyway, I'm going to link these. They're the cool computers file. I think they're really useful. Okay. How then we give this a go? Because that is, folks, what we're now going to try with our lab. So we're now going to go and give exactly that a moment. Securing data in Amazon S3 using Macy and KMS. I think that's probably a good chance to go and give this a bit of a whirl. So we talked about Macy this morning. We've now looked at KMS and actually looked at what it is that it does, the algorithms employed by KMS. What say you a chance to use that all together in one fell swoop? I'm going to link this up for yourselves, and if mentors as well, I know Sean's with me. Can you please go and check, does that link actually work for yourselves if you went to go ahead and click it? So we're going to have a Macy.
Yeah, it works.
Yes, okay, perfect. But sometimes there are part of plans, I'm not too sure if it does. Wonderful. Yeah, this is a good one. So we're going to be using Macy again. That's going to be the machine learning algorithm that's going to sweep your buckets for any PII to identify any personally identifiable information that's stored in your objects. Then you master data with downstream AI systems. Okay, finally, you can rotate the key material too. Okay, so KMS makes the rotation of the key ciphers so that you don't have to either, just simplifying or managing that on your behalf. Cool, cool, cool. I think the rest of it should be self-explanatory. I believe this one will take about an hour. So given where we are now in the time of day, why don't we do the lunch in the lab in one fell swoop? So we'll do this plus 1 hour lunch, which brings us back to 1:10, I believe, to then look at S3 and other encryption methods. What say you folks? Would that be okay? So we come back in 2 hours. Perfect. Before we go, any questions, any thoughts, any queries, anything at all on this? And I will briefly just send computer file. If you do get a moment to to watch it, it's a very, very interesting. I thought it was interesting, at least. Okay. You don't have to find it interesting, but I did.